Hello everyone, it's Abdul Babatunde Kukwala again for this channel, Nobel Process Designer. You are all welcome to another exclusive video from our channel. Today I want to show you guys a simulation model that I created for a cogeneration thermal desalination plant, supercritical water desalination plant. The plant is to generate electricity and clean water for agricultural and human use in arid region. So we are going to be using Aspen HYSYS. We use Aspen HYSYS to develop the model for the plant, and we use it to analyze the plant performance, the economic analysis, the energy analysis, thermodynamic analysis, efficiency, life cycle analysis of the plant. So the plant basically source water from the seawater. So this can be from the sea, maybe from the bank, or a very large with pipeline from the sea that pump water to the. So this kind of plant is located at the shore. You understand? So then the seawater is divided into two. One is used to cool down the desalination water. Then, because this kind of plant is a power plant and it needs a lot of cooling for the power plant. So with that in mind, you'll be taking a lot of water in, and you split into two. One is returned back to the sea, and I make sure that the temperature difference of the water is not too large. You can see from 30 to 37. You understand? And when you check the composition of the seawater, you see it is 0.035 weight percent with that's 3.5 weight percent sodium chloride. You understand? Then the one that want to be used in the process is taken. In this case, the capacity that we want the plant to be processing is 5,000 meter cube per day seawater. So then you take in the water, you pump it to a very high pressure, more than supercritical condition, and you send it to this supercritical heat exchanger. From this supercritical heat exchanger, you send it to the boiler to increase the temperature to a very high supercritical temperature. Then when it reaches this temperature, it's separated into supercritical water, which is very pure, because at supercritical condition, sodium chloride separates rapidly from water. You understand? So they tend to partition themselves into liquid phase, while water will flash out. You understand? So from there, you can use a separator to separate it. The separator will be designed in such a way to take care of the condition, that extreme condition. So it can be like a stainless steel separator. You understand? So this is the key for the desalination process. Then you have a brine, highly concentrated brine. If you want to see the brine, you can see at this condition, you see the mole fraction of the brine is given to be 0.69 and 0.3. These are highly concentrated brine. There is no desalination process that will give this kind of highly concentrated brine. You understand? So, and one of the efficiency of the advantages of using this supercritical water is to produce dry salts. We want to produce dry salts, and we use a zero liquid discharge process, as you can read from literature, from most of the literature in the technology. I talked about the technology. I think for all these, I think there's one here. There's one here. All these panels. They talked about the technology as being a potential for zero liquid discharge technology. That is, there is no liquid brine problem in the plant. So the salt can be used for human consumption or sold, you understand, or for production of another chemical, you understand. So it's a very efficient process. Then the problem with the using the salt is, you can see this is not a typical separator. I had to create this separator from scratch by myself using Aspen custom modeler to create the model for it, and the flash subroutine calculation, the phase calculation, the vapor liquid model that I'm using to calculate the phase partitioning is based on the correlation, because if I try to use the property method that is available in Aspen HYSYS or Aspen Plus, I'm currently using electrolyte NRTL property method for the model. But if I try to use that for the supercritical condition of that separator, it will not work efficiently. It will give you a very erroneous result. You understand? That will bring down the accuracy of the model. You understand? So I have to develop a subroutine in C++ for the model. I think if you go to Thermo here, I had to develop a for the model and integrated it into Aspen Custom Modeler, and the formula for this, that the theory behind the subroutine is given by regressing this data that is reported from Beckhoff and Pizza. All this thermodynamic, all this equilibrium data that is recorded from Beckhoff and Pizza for this vapor equilibrium data for supercritical condition brine. You can see the critical condition, you understand, or for high pressure and high temperature water and salt solution, you understand, make sure. So I have to do that for the Aspen Plus, Aspen Custom Modeler. So after creating the code in Aspen Custom Modeler, I used the flash calculation for it, and I was able to integrate it to Aspen Plus and get my result for the separator performance, the way this separation is going to be in the separator. So from here you can see the composition that will be given off. This is a very pure water, and you have this composition. If I'm using the Aspen property, the NRTL, the composition of salt will be very low. You understand? And it will not be very accurate as expected for that supercritical condition. And you can see the equation of the salt, the parameters, the variables is the temperature in, pressure in, the temperature that we are using in case you want to change the temperature, you understand. Then the triple point temperature of the mixture at this temperature, because this temperature is around 500 degrees Celsius, you understand. So this is the critical point pressure that will give for the mixture. And you can see, mind you, this is not the pressure of the water, it's for the salt and water solution, which is a very special chemical, you understand. If you are just using only water, you can use the ASTM steam property to give you a result, even for supercritical water. But when you add salt to it, the property became highly non-ideal. You understand? The non-ideality of the property is very high, and most model does not work for it. Even when I was working on the system, I tried different methods using high temperature equation of states. It's very difficult to cubic cross association property. I was trying to regress the property, but I was able to just use this method for the correlation, and I'm getting the result. And if you get the correlation code, this is the phase diagram for that the correlation predicts, and it's very accurate based on most of the experimental data that I measured for the system. And you have the equation for the code. All this equation is written into the code, and for the subroutine that make the process very fast. Because if it's not fast, it's a very difficult model. It will still be it will not be easy to use for modeling. You understand? So you have the vapor fraction, liquid fraction, the amide fraction, that is the solid salt fraction. Then if there is any precipitation or something, then this is for the heat, in order to equilibrate the model calculation and the Aspen property calculation, so that there won't be any mismatch. So I have to send the pressure, the state property, back to Aspen HYSYS, sorry. So this is the difference in energy, you understand. So then after you get your high concentration brine, you send it to this 4-stage flash to generate more steam, which is used to power a forced circulation evaporator. To see the forced circulation evaporator, I can open it as a flash. So then the forced circulation evaporator, you have the brine, we flash again to get more steam. and the brine is circulated in this evaporator to this evaporator tube, and is being heated in the tube using the steam that is produced from the first stage plant. This steam that's produced here is used to heat up the brine in the first evaporation, so that you get the processes. You are not using any other external energy to make the process efficient and the likes. So you get your brine out here. You understand? The steam is also very pure, and you have even if it's not, you still have energy. You cool it down in the condenser. So the purity is what we need to get our purified water, and this all the steam that is evaporated, they are very pure. You understand? So we are able to get our evaporator water from it, and the dry salt is coming up here. If you check the composition of the dry salt, it is very high composition. You cannot find a salt from a desalination plant that is as high as this. You understand? So this is very good. So, and then the cooling water that is used to cool down the salt is returned. You understand? These are the waste cooling water, so it's still having the same composition as the feed composition. So you don't need to do any purification for the brine, for the danger or something, or the pollution to the sea environment. So it's still the same composition. So this process is very good. You understand? And I even did the color coding for the line, so you can see this is for the ultra pure water, like even less than 100 ppm. You understand? So this water is less than 100 ppm. Then you have the one that is like 1% salt. This is 10% salt, 50% salt, 70%, 90% salt, and more than 90% salt, as you can see for the dry salt here. So you can measure, see the range, how the salts change from normal seawater composition salinity to high salt composition, concentrated salt concentration, and then the dry salt. You understand? So you can see the levels at this is coming from, and you measure your profile. Then this process, like I said, is a power plant that is attached to it in order to make the process more efficient. So the supercritical water that is produced is used to drive the turbine of a steam turbine, and you generate 14.88 megawatts of power from here that can be used or sold to the grid. Then the condensate is the water that we are purifying. It's very pure. That's the water that you have at your main desalination plant, and it's mixed with the evaporated water. You understand? So if you check the composition, it's also very pure. Also very pure. You can see it's also very pure. So then you send it to the supercritical heat exchanger to exchange the heat with the feed, so that you won't be burning a lot of fuel. You understand? Then you have the condensate, the condenser, to condense the water into liquid form. So the water is steam here, then it becomes 40 degrees when it is where is this liquid water? You can see liquid water, aqueous phase. So the steam is also, there is a gas turbine system that was attached to the system to generate, to provide, like, so that, because there's a model that I did where I was even burning because this is a one strip burner, that means there is no circulation or stuff like that. So I was burning the fuel there. So in order to increase the efficiency of the plant, we added a gas turbine to the system, where we have the two. This is the natural gas feed to the gas turbine. That's the main feed fuel for the process, for the power plant process, the cogeneration power plant project that produce water and electricity. So this is the air stream. It is compressed here in the compressor, air compressor. Then this is the burner, where the fuel is burned with air to generate high thermal energy to drive the gas turbine from the flue gas energy. You can see very hot temperature. Then the energy is used to drive the turbine shaft and the compressor shaft. You understand? And the net energy, you can see this one is 105.5 megawatts. This is for 3 megawatts. So the net will be added to this steam turbine to produce total power from the power plant. And the flue energy is used to, the flue gas from the gas turbine is used to drive this power plant, desalination plant, and it's sufficient. sufficient to drive desalination plants, and you are able to get, you can see this 99.65, and this is greater than the inlet temperature of the power plant. So with 5-degree difference minimum temperature approach for safety issue, you understand. And then you can also crack up the plants so that you get more energy, but that will be the wasted energy. But this is evidence that the plant is will be able to work, you understand, for this kind of configuration, and you can expect this kind of performance for the plants when you build the plants, or when you go more research on the process. So this is a very good process for cogeneration thermal desalination plants, where that produce salt, electricity, and desalination water. I did a extensive research on this, on getting the, how will I call it, getting the efficiency, the power, the cost, and or on the performance of the system. I was able to see the influence on the system. So if you are working on something similar, I would like us to discuss. So thank you very much for your time. See you on the next one.